In this chapter, we will look at the mathematics of what causes an endo. You'll see a detailed illustration worked out, and then we will answer the question, does the wheel sacrifice the rider to protect itself? While stopping forces you're learning, for an in-depth knowledge you're yearning, don't quit till you're through as you strive to pursue the opposing moments of turning. Let's go back to this scenario when the rider is trying to stop the bike in 3 seconds. 1001, 1002, 1003. The attempt to abruptly stop the bike will fail if the road surface is incapable of delivering the required 515 newtons of stopping force, and particularly the front wheel, which has to deliver 2/3 of that. There are two typical scenarios that can cause the braking effort to fail. First of these is when the rider goes over the handlebars, and it's worth our time to take a careful look into the physics of this. We can get a pretty good sense of when this can happen by consulting the book written by Dave Wilson, whose photo is there standing next to me, taken when I visited him on more than one occasion. I'll show you a quote from the book with the results of a calculation and then show you how the calculation was done. We'll be using all of the numbers from Dave's calculation with my graphics. A deceleration of 0.5 g, 4.91 meters per second squared, is almost the maximum that can be risked by a crouched rider on level ground before he risks going over the handlebars. Of these equations that we looked at briefly before, the solution to this problem is in this one. Because we know that the turning moments around the front wheel have to equal 0, we can solve this equation here to find out when the rider will go over the handlebars. And we're going to use the same example as Dave Wilson uses in page 244 of his book. Distance B becomes 42 inches or 1,067 millimeters. The combined weight of the bicycle and rider is equal to 196 pounds, and that gives me a mass of 89 kilograms. The magnitude of this force at the center of mass is going to be equal to 89 kilograms times the gravitational constant, which is 873 newtons. Before the onset of braking, more of the weight of the bike and the rider is over the rear wheel than the front, and if we distribute it like this, 40% on the front, 60% on the rear, that means the force on the front wheel is 353.5 newtons, and the force on the rear wheel is 519.5, totaling 873. There's a little bit of a rounding error there, so if you're sitting there with a calculator trying to catch me at a math error, let me change those percentages to 59.5% on the rear and 40.5% on the front. Because the forces pushing down from the bike and the rider on the ground are the same as the forces of the ground pushing up, I have just calculated that force and that force. We show those here, and just to be perfect, we will adjust the length of those two vectors to this. Distance x here is 17 inches or 432 millimeters. Distance y here is the distance of the center of mass above the ground, and that is 45 inches or 1,143 millimeters. B minus x is 1,067 millimeters minus 432 millimeters, and that gives me 635 millimeters. we know that as we brake, weight, which is the force, is transferred to the front wheel from the back wheel. If I brake too hard and too fast, at some point the downward force of the bike and rider on the rear wheel will become zero, and so will the upward force from the ground. At which point this term here, which contains the upward force on the rear wheel, becomes zero. If I rearrange this equation, I get this. About the front wheel at this point, the clockwise and counterclockwise turning moments are equal. And even the slightest increase in the braking force results in this. It's worth noting that in most cases, once you start going over, it becomes self-fulfilling and can't be stopped. This expression can be further rearranged to give me this. And taking Dave Wilson's calculations to a conclusion, this force, which is also here, times this distance is equal to this force times this distance times the ratio of the acceleration of the rider divided by the gravitational constant. This is the expression with the numbers substituted. Here is the solution to that equation, which says that if your negative acceleration or deceleration due to braking is more than 0.56 Gs, you're going over the handlebars. Which is why we said before that a deceleration of 0.5 Gs is almost the maximum that can be risked by a crouched rider on level ground before he risks going over the handlebars. If we look at the equality of these turning moments here, we can make a few more observations. The mass of the rider is unimportant because the mass term cancels out. But the height of the rider will matter because a taller rider means that the center of gravity is going to be higher, and that means y is greater, and that means the right-hand term of this equation goes up. In order to maintain equality, the left side has to go up as well, and that can only happen by increasing the distance b minus x, which I can increase by either increasing the wheelbase or moving the seat further back. The concept here is the most important thing to understand, so we can get rid of all these numbers and just make sure we understand what the concept is. At the instant that I start to brake, if 60% of my weight is on the rear wheel and 40% on my front wheel, then 60% of the braking will come from the rear wheel and 40% from the front wheel. But the turning moment around the front wheel causes the weight and braking force to shift forward, and we see this picture. Finally, at this point, we're ready to go airborne. And one more time for fun. If I'm not careful, I can find myself going from this to this to this to this. MA divided by mg is here, and that becomes just A over G, and that we know from our calculation that to avoid the risk of going over the handlebars, that ratio has to be equal to or less than 0.5. If my velocity is 20 miles per hour, which is 8.94 meters per second, this is the equation for my acceleration or deceleration in this case, and I want the value of acceleration to be equal to or less than 4.91 meters per second squared, which is 1/2 of g, or the gravitational constant. That means my time has to be equal to or more than 1.8 seconds. Now there is a simplification built into this calculation that can be misleading, and it's this. The time of 1.8 seconds is assuming we have a constant rate of deceleration, which means an easy application of the brakes. But the fact is, if you're going from 20 miles an hour to zero in something less than 2 seconds, you're probably applying some pretty heavy braking. And we really should be looking at this from a standpoint of calculus to determine the instantaneous acceleration, which is the instantaneous change in velocity per time, and that initial acceleration can be very large, leading possibly to an endo unless you go into a skid, and that will depend on the friction between the tires and the road surface, a topic that will be taken up in the next chapter.